Okay, so in this video, we are going to consider another example of the subspace theorem. So far we have considered examples of a subspace in R4, so vectors with 4 components, then a subspace of the space of 2 by 2 matrices, being the space of 2 by 2 symmetric matrices, and here we'll consider a vector space of functions. So we will let W be the space of polynomials in P3. So P of x is a polynomial. It belongs to P3. If you remember, P3 is the space of polynomials of degree at most 3. So constant polynomials, linear polynomials, quadratic and cubic, but nothing of higher degree than 3. And we will take the polynomials of degree at most 3 that have as a critical point x equals 1 and say x equals negative 3. So the derivative of p at 1 will equal the derivative of p at negative 3, and they're both equal to 0. So if you think of it, we take polynomials of degree at most 3 for which x equals 1 and negative 3 are critical points. As always, if we hope to decide whether or not what we have is a vector space, if possible, we want to show that this is a subset of a known vector space, where we know that Pn for any n is a vector space, and since we take polynomials in P3, what we have is a subset of P3. And we know that P3 is a vector space. So we can now use the subspace theorem. We do not have to prove that the space W satisfies all of the 10 axioms, only the 2 closure axioms. So let's check closure under addition first. So we take 2 elements in our space. The elements are polynomials. We can call them, say, P of x and Q of x. And because they are elements of the space, they must satisfy each the given conditions. So we know that the derivative of p at 1 equals the derivative of p at negative 3, which equals to 0. And the same is true of q. As q is a polynomial in W, it must also have a derivative at 1 and negative 3 equal to 0. So the derivative of q at 1 equals the derivative of q at negative 3, which is equal to 0. And what do we want to show? We want to show if we add p and q, we have a polynomial that also lies in W. Hence proving closure under addition. If we take 2 elements of our space and we add them up, the result is still an element in the space. Well, let's see. Clearly, if p and q are in W, they are in P3, so they both have degree at most 3. And so if you add 2 polynomials of degree at most 3, the sum is also of degree at most 3. What we have to show now is that x equals 1 and x equals negative 3 are critical points of our function. So we find the derivative of p of x plus q of x at x equals 1, right? If you recall, the vertical bar means that we will evaluate the function at this point, right? So we find the derivative of p plus q. We know this is simply the derivative of p plus the derivative of q, as the derivative is linear. And now we can evaluate at x equals 1. We get p prime of 1 plus q prime of 1. But we know that both of these are equal to 0 by assumption. 0 plus 0, the result is 0. Therefore, at x equals 1, the derivative of p plus q is equal to 0. So x equals 1 is a critical point of p plus q. Let's prove that x equals negative 3 is also a critical point of p plus q. We differentiate and evaluate at x equals negative 3. Once again, this is the derivative of p plus the derivative of q at x equals negative 3. We evaluate, so we get p prime of negative 3 plus q prime of negative 3. But by assumption, x equals negative 3 is a critical point of p and q, so these are both equal to 0. And we get 0 plus 0, which is equal to 0. And so you see, x equals 1 is a critical point of p plus q. X equals negative 3 is a critical point of p plus q. Therefore, p plus q is still a polynomial in our space. So this proves that we have closure on their addition. Let us now prove that we have closure on their scalar multiplication. So we take an arbitrary element of our space, therefore a polynomial in W, where x equals 1 and x equals negative 3 are both critical points, and so p prime of 1 equals p prime of negative 3, which equals 0. And we must take also an arbitrary real number, say k. And we want to show that k times p of x will also be a polynomial in our space W, hence proving that we have closure on the scalar multiplication. Well, again, clearly, if p is in W, it is a polynomial of degree at most 3. And if you multiply p by a constant k, the degree is still at most 3. So we simply have to prove now that x equals 1 and x equals negative 3 are critical points of k times p. So we look at the derivative of k times px at x equals 1 first. Well, the derivative is linear since k is a multiple, a scalar multiple of the function. The derivative of kpx is simply k times the derivative of p. And we now evaluate at x equals 1. We get k is a constant, so k is always k, times p prime of 1, which is equal to 0. So any real number times 0 is 0. And so x equals 1 is a critical point of k times p of x. Let's check that the same is true for x equals negative 3. The derivative of kp of x, as we have said before, is k times the derivative of p of x. And now we evaluate at negative 3. K is always k as it is a constant times the derivative of p at negative 3. By assumption, negative 3 is a critical point of p, and so it's equal to 0. We get k times 0. And again, for any real number k, k times 0 is 0. And so you see that x equals 1 is a critical point of k p of x. X equals negative 3 is a critical point of k p of x. Therefore, k times p of x is an element of our space. So we have now proved closure under scalar multiplication. And so, by the subspace theorem, W is indeed a vector space. Now, since we know we have a vector space, let us find a basis of this space and its dimension. And as always, to find the basis of a vector space, we have to consider the elements explicitly. So let me just rewrite what W is. So now we know we have a vector space, and it is the vector space of polynomials of degree at most 3, so in P3, where the derivative of P is equal to 0 at x equals 1 and x equals negative 3. So P prime at negative 3 equals P prime at 1, which equals 0. And so you see, once again, what we have is implicit. We're saying that we have as our elements of our space polynomials of degree at most 3, for which x equals 1 is a critical point and x equals negative 3 is a critical point. Well, now let's look at the elements of our space explicitly. So P of x is a polynomial of degree at most 3. So it will look like some constant plus some multiple of x plus some multiple of x squared plus some multiple of x cubed. Whoops. A, B, C, D. And we stop with degree 3 because that's what P3 is, the set of all polynomials of degree at most 3. So P of x must be of the form constant plus linear term plus quadratic plus cubic term. And now let's see how the conditions will affect the way our polynomial looks like. We need to find the derivative, so P prime of x, let's differentiate. The derivative of a constant is 0 plus b plus 2cx plus 3dx squared. This is the derivative of p. And now let's evaluate both derivatives at at x equals 1 and negative 3. So p prime of 1, let's replace x by 1, gives us b plus 2c plus 3d, and this equals 0. And let's evaluate the derivative at negative 3. So p prime at negative 3. We now replace in the derivative x by negative 3, which gives us b. Negative 3 times 2, negative 6, so negative 6c. Negative 3 squared is positive 9, times 3 is 27, so plus 27d, and this is equal to also 0. And now look at this. The only polynomials in W must be so that the coefficients a, b, c, d of our polynomial are solutions of these two equations. And what we have here is a linear system. You see, the only way that p of x equaling a plus bx plus cx squared plus dx cubed has a derivative of 0 at 1 and negative 3 is if the coefficients of the polynomial are solutions of the linear system. Well, again, this is implicit. We're asking what are a, b, c, d equal to, and now we're saying that they are solutions of this linear system. Well, let's solve it, and then we will have found the elements of our space explicitly. Let us look at the augmented matrix. A, even though it's not here, is, but it simply has a coefficient of 0. So we'll look at A, B, C, D. The first equation will be 1, 2, 3. The second equation, the second row, will be 0 again for A, 1, negative 6, 27. Well, we already have a leading 1. Let's do row 2 minus row 1 to kill the entry below. Zeros will always remain zeros. We are only changing row 2, so you can recopy row 1. 1 minus 1 is 0. Negative 6, negative 2 is negative 8. 27 minus 3, 24. We will now get our second leading 1 by multiplying row 2 by negative 1 over 8. As always, we copy row 1 as we're not changing it. So you'll get 0, 0, 1, negative 3, as 24, sorry, is 3 times 8. We have our second leading one. Let's complete, the reduction by doing now, killing the entry above our second leading one by doing row 1 minus 2, row 2. This will complete the reduction. We are only changing row 1, so you can recopy row 2. Let's complete the operation. So row 1 minus 2, row 2, these will stay the same. Row 2, 2 minus 2 times 1 is 2 minus 2 is 0. 3 minus 2 times negative 3 is 3 plus 6, which is 9. And this is also 0. And now we have the reduced first echelon form of our matrix. We can write the complete solution set. Let me write this here. We had our 4 coefficients, a, b, c, d. As you can see, a and d don't have leading ones, so they are free variables. Say a is s, d is t. And now if you solve for c, c will be positive 3d, which is t, so it's going to be 3t. And if you solve for b, you will get negative 9d, negative 9t. And s and t are parameters, so they can range over all real numbers. And now we have solved for our coefficients. Well, let us look back to our element, right? We were looking for a way to describe polynomials explicitly in W. So we didn't know what a, b, c, d were equal to, but now we do. For any choice of s and t, a must be s, b must be negative 9t, c must be 3t, and d must be t. So we can replace now. So our polynomial, p of x, must equal a, so s, plus b, x, so negative 9tx, plus cx squared, so plus 3tx squared, plus dx cubed, plus tx cubed. And as always, once you have found a way to express your element explicitly, so the only variables here are s and t, and they are parameters, free variables, to extract a set of generators, you simply have to split the parameters. So let's do so. Well, this is s. So we have s times 1, plus, if you split the t, plus t times, if you factor t from these, you'll have negative 9x, positive 3x squared, positive x cubed. And so you see, every polynomial in your space is a linear combination of this polynomial, which you can call v1, your first generator, plus a multiple of this polynomial. This is your second generator, and you can call this one v2. Then you see, as every polynomial of your space W is some multiple of v1 plus some multiple of v2, and they are polynomials, these two elements are generators. So what we have now is a possible choice of a basis. The span of v1 and v2 is all of W, our entire space. So we have generators. To prove that the set v1, v2 is a basis, we have to prove that the two vectors, the two elements, v1 and v2, are linearly independent. And as always, we go back to the definition of linear independence. Let me just rewrite the two vectors. v1 is the constant polynomial 1, and v2 is a cubic polynomial. And I'll write the cubic term first. It was x cubed plus 3x squared minus 9x. And so we want to prove that these are linearly independent, so we consider as always a linear combination of our vectors giving the zero vector, and we want to prove that this equation has only the trivial solution. Well, let's compute this. So we'll have c1 times 1 plus c2 times v2, which is x cubed plus 3x squared minus 9x. If you multiply out and rewrite in canonical form of a polynomial, so you will get c2 times x cubed plus c2 times 3x squared plus c2 times negative 9x and finally the constant term plus c1. And if you think of it, this is equal to the zero vector, but the zero vector is the zero element of your space. We have a space of polynomials. The zero element is the zero polynomial. This must be 0 as the zero polynomial, therefore 0 for all real values of x. As the zero polynomial is the zero element of our space. But if you think of it, look at this polynomial, right? It is c2 times x cubed plus 3c2 times x squared minus 9 c2 times x plus c1, and this must be the zero polynomial, therefore equaling 0 for all real values of x. But we know that if you have a polynomial in canonical form, so constant term plus multiple of x plus multiple of x squared plus multiple of x cubed, the only way for this polynomial to be the zero polynomial, therefore equal to 0 for all values of x, is if every coefficient is equal to 0. So c1 has to be equal to 0. The multiple of x, negative 9c2, must be 0. But if negative 9c2 equals 0, c2 must be 0. And we could keep going, right? 3c2 must be 0. Therefore, c2 is 0. c2 times x cubed, c2 must be 0. But we already knew this. And so you see, the only way to solve this equation is if c1 is 0 and c2 is 0. Therefore, this equation has only the trivial solution. And therefore, by definition, this proves that the vectors v1, v2 are linearly independent. And so indeed we have a basis. v1, v2 are generators of the space. This constant polynomial, y equals 1, so a horizontal line, this cubic polynomial are generators, and as they are linearly independent, they form a basis of our space. Let me write them explicitly, right? v1 was just the constant polynomial 1, v2 is the cubic polynomial x cubed plus 3x squared minus 9x. And this is a basis of W. And now we can also answer the question of what is the dimension of W. The dimension of a vector space is, as always, the number of elements in a basis. And our basis contains two generators, and so we have a two-dimensional vector space. And you see our conclusion is P3 is a four-dimensional vector space. W is a subspace of P3, and it is a two-dimensional vector space. And so you see, whether you deal with vectors explicitly or matrices or polynomials, it really is just the same. Try to use as much as you can the subspace theorem. Then, once you know you have a vector space, to find a basis you have to find the elements of your space explicitly. To extract generators, split the parameters, the free variables, and don't forget at the end to prove that you have linear independence. And this is always done going back to the definition of linear independence. And that's it. One last comment is, if you ever try to prove that something is a vector space using the subspace theorem, if one of the two closure axioms fails, you can stop and you do not have a vector space.